All right, class, welcome back to part B of this relatively short lecture on parametric uncertainty, specifically polytopic and interval uncertainty. In part A of the lecture, we introduced two concepts, robust stability and quadratic stability. Robust stability being defined in terms of the representation of the system, in that the eigenvalues of the system are negative for all possible values of the uncertainty. And alternatively, quadratic stability, which required the existence of a common Lyapunov function for all possible systems within the uncertain set. Right. And that Lyapunov function condition was expressed specifically in terms of an LMI. So an LMI, however, which has to hold over a set, over an uncertainty set. In this way, the notions of quadratic stability and stability over a polytope or stability over an interval are somewhat different than the LFT representations, where we shuffle off the uncertainty into a block and try and deal with it separately. Rather, in this case, we are simply looking for a Lyapunov function which holds for every possible value of the system, right? So we have a set of systems, and we want to search for a Lyapunov function which works for all of the values in that system set. Now, I said this was expressed as an LMI, of course, but it's really expressed as an infinite dimensional LMI, in that it has to hold for all, right? For all values of, in this case, delta A, although we'll have different representations of that, for all values of delta A in a set. And the set is infinite, right? There's an infinite number of points. So if it's a polytope, for example, right, there's the vertices, but then there's every point of delta A inside the polytope. So it has to hold an infinite number of points. And so the logical question is, how does one enforce such a condition? So the first result in this part B is really the only theoretical result, or the only sort of fundamental result we have, which allows us to enforce this LMI, or any LMI, really, over a polytope. So specifically, here we have a polytope. And we have an LMI which we would like to enforce for all values on that polytope. We can also have an objective function or something like that, but we're just looking at the feasibility problem here for now. So what we're trying to enforce, right, is that this is an LMI, and this is a general form, right? This is we can represent almost any LMI in this form. So nothing specific about that LMI. It's not it holds for any LMI. Doesn't even have to have anything to do with system stability or anything like that. So it's just a general form of LMI. So an uncertain LMI, an infinite dimensional LMI, whatever. However, the critical point being it being defined over the polytope, where a polytope being a set which has vertices, and you're taking the weighted average of those vertices, right? So it points in here. Right. So what this theorem tells us is that this LMI is feasible. It's true if and only if the LMI holds at the vertices of the polytope. So notice the sum here, we have that this is just allows us to put a bunch of terms in here, right? So this I equals 1 to L, for example, not K. Where but the delta J's here, and J is a different index than I. It goes from 1 to K, right? So there's K vertices in this polytope. So for example, if you had if you're taking the weighted average or the polytope based on measurements, right, and you had K measurements, right, there would be K vertices. Right. So what this is saying is that we can enforce an LMI over a polytope by enforcing the LMI at all the vertices of the polytope. So this actually gives us, of course, K separate LMI constraints, but as we know, we can stack LMI constraints into an optimization problem, and it doesn't really change the structure of the LMI at all. So we can have L1, and the delta i's are given, right? They're like, we know what the vertices of the polytope are. Right? Delta 1. So let's just make just one constraint. So if we had a constraint like this, we would add an LMI constraint like that, and then we'd add to it another LMI constraint, delta 2 r less than 0. And if we had more vertices, we would just keep going and add more LMI constraints to our YALMIP code or what have you. Okay. So that seems like that's a very interesting result. It takes an infinite dimensional LMI, right, which has to hold an infinite number of points, and it converts it to a finite dimensional LMI, so with only k constraints. That's a very powerful result, and there aren't many like it in the literature, right? There's not many ways of enforcing these kind of infinite dimensional LMI results. This is really the only one, in fact, that I can think of right off the top of my head. Although we'll definitely extend this result in several directions, most obviously the case of interval uncertainty. But the interval uncertainty will come back and just use this result again. So it's a very important theorem. Theorem 4. Okay. The proof of it is actually remarkably simple. So it's necessary and sufficient. So how does one prove it? It's really quite obvious if you think about it, but maybe not you hadn't thought about it, so maybe it's not so obvious. So I'll just mention it, right? So obviously, so this is 1, right? 1 and 2, right? We want to show their equivalent, so we want to show 1 implies 2, and we want to show 2 implies 1. Show 1 implies 2 is really quite obvious, right? If the LMI holds at every point in the polytope, then obviously it holds at the vertices, right? So that's we're done with that. The other direction, of course, seems much harder, right? If it's holding at a not finite number of points, how do we prove that it holds for all the weighted averages of those points? Okay. That's actually, it's not too hard to show, in fact, and I show it here on 2 lines. It's not terribly difficult, right? So first of all, we say, suppose this LMI holds at the vertices, right? Right. So if it holds at the vertices, right, then we have that this is true, right? So specifically, h plus some Li delta I j Ri is less than 0. Okay, so that's true. Now, what we're going to do is say that we have any point in the set, right? In point 1. So for any point, any value of delta in that convex polytope, right? So any delta in that polytope can be represented, right, as the sum of the weighted averages of those vertices, right? So we know that there exist alpha I such that, right, delta equals this summation, right? And those alpha I satisfy, right, just by the definition of the convex hull, the alpha i's are greater than 0 and they add up to 1. So what do we do with that? Well, first of all, we can multiply hi by the sum of alpha I, right? Because that's just equal to 1. So we just multiply that term over there by alpha I. And then we notice that these alphas are scalar, right? So we pull out the summation out of this term. And we pull out the alphas out of that term as well because they're scalars, so they can commute with matrices. So we pull them out as well. Right? And so we've got the sum on the outside of this term, and we've got the alphas on the outside of that term. And then, of course, because we multiplied 1 by this h, right, it's got its own sum of alpha i's, and so we pull that out as well. Okay. So what we've got here is the sum of a bunch of alpha i's times the LMI at the vertex, at each vertex, right? LMI at vertex j, right? And of course, we know that the LMI holds at the vertices, right? So each of these individual terms are all greater than or equal to 0. So if we add a scalar, multiply that by a positive scalar, it's still positive. And if we sum up a bunch of positive matrices, it's likewise still positive, right? As the sum of positive matrices, pi is greater than 0, and the sum of alpha I, pi, if pi are greater than 0, is also positive, right? So that shows that at any arbitrary point in the polytope, we can prove that the LMI is feasible by using the weighted averages of the LMI at the vertices. Right? So that's a relatively short proof, but very powerful in that it allows us to reduce an infinite dimensional LMI to a finite dimensional one. So the rest of this lecture is really just applications of that very fundamental result in several directions. First, we do an easy one, which is quadratic stability over for polytopic uncertainty. Right? So specifically, right, we want for quadratic stability, it's defined this way. We want a plus delta p, right, plus p a plus delta to be negative definite. That is, we want p to be a Lyapunov function for every delta in delta. Right? But delta here, we take it to be the convex hull of these vertices, and so we can just apply the LMI, or this LMI, at the vertices, and we have a necessary and sufficient condition for quadratic stability over the polytope. Right? Necessary and sufficient by highlighting that if and only if part right there. So no conservatism here, right? This is if and only if. So we have a finite number of LMIs, which we have to enforce, right? So you just keep adding them on to your constraint structure in YELMIP, and you get an LMI for quadratic stability over a polytope. Right? So this is a relatively straightforward application of the theorem on the previous slide, and it's a relatively easy to enforce, conceptually easy to understand LMI for robust stability over a polytope. Right? This parametric, the polytopic and interval uncertainty, is really the easiest form of robust control to understand and interpret. It has limits, but within it does very well, and it does it with relatively little conservatism. Note that there is no, of course, equivalent, as I mentioned at the end of the previous part. There's no equivalent conditions for which don't involve LMIs. Right? This is not unlike optimal control, where many of the results can be expressed using systems theory without LMIs. The robust control framework is really quite intimately tied in with LMIs, and there's really very little what you can do without LMIs in that context. Okay. Quadratic stability, remember, itself is expressed as an LMI condition. Mostly because conceptually it's just searching for a Lyapunov function, and Lyapunov functions, quadratic Lyapunov functions, are naturally stated as LMI conditions. So the next obvious extension is to the case of interval uncertainty. Right? So where we have our uncertain parameters lying in an interval, and I've just scaled those to negative 1, 1. I could have also scaled them to 0, 1, but I chose negative 1, 1 because the notation is a little bit easier. So the key here is to note, or is to visualize this set, right? The set of uncertain parameters, right? So what does the set look like, right? Well, if you have a single uncertain parameter, delta, right? Well, it's just the interval from negative 1 to 1. Okay, what happens if we have another uncertain parameter, delta 2? Well, it's the interval from -1 to 1 in delta 1, and then the interval from -1 to 1 in delta 2. Right? So that. So if we fill in those allowable values of delta 1 and delta 2, sorry, it doesn't look much like a delta, then we get a square. Right? If we keep going, right, and we have, let's make this delta 1, this delta 2, and delta 3, right, then the set of possible uncertain parameters is the extension of the square to 3 dimensions, which is a cube, right? So this point on the cube is, for example, here they do 0, 1, so I'll just like do that. That corner is 1, let's see, 1, 0, 1. That's delta 1, delta 2, delta 3. This corner here is 1, 1, 1. Sorry, I went off the screen there. 1, 1, 1. This corner here is, they make it 0, 0, 0, but, well, okay, we'll keep it 0, 0, 0. Right. So the important point is that a cube is a polytope. That sounds very weird. But it is the convex hull of a set of points, right? So point here, point here, point here, point here, point here, point here, point here. So a cube in 3 dimensions, for example, is the convex hull of a set of 8 points. 1, 2, 3, 4, 5, 6, 7, 8. Right? Likewise, in 2 dimensions is the convex hull of a set of 4 points, and 1 dimension is the convex hull of a set of 2 points. Right? So the hypercube, or the interval uncertainty case, is actually a special case of polytopic uncertainty, where unlike in in the case of polytopes, right, we had maybe the number of vertices was given by, say, the number of measurements. Here the number of vertices is given by the number of vertices, the number of uncertain number of constraints, right, the number of vertices of the polytope are given by the number of vertices of that hypercube. Right? So whereas in the original formulation, the interval uncertainty case, say we had, for example, 2 uncertain parameters. When we convert this to a polytope, we're going to get 2 to the, say, if there's like k of these, I equals 1 to k. Okay. When we convert the hypercube to a polytope, we're going to get 2 to the k vertices. Right? Right. So these are representable, right, as vertices. And so we can say, we can just skip the whole conversion to a polytope and just state that the LMI, infinite dimensional LMI, the quadratic stability condition, is satisfied if the LMI holds at all the vertices of the polytope, or of the hypercube. 1, 2, and all 8 in this case. And of course, 4 dimensions, right? If we had 4 uncertain parameters, it would be 2 to the 3. No, sorry, 2 to the 4. So it would be 16 vertices. Right? So basically, you've got, if this is your interval representation, let's not actually directly convert it to the polytope representation. You simply need to enforce this LMI at every possible value combination of the delta i's, right? So for you need to enforce, you have one LMI, say there's 2 dimensions, right? Delta 1, delta 2, right? You have one LMI at 1. Let's make it negative 1, 1, negative 1, negative 1, negative 1, 1. 1, 1, and wait, I missed one, and 1, -1. Sorry, there's a bit out of order. So actually, if I'm doing this in lexicographical ordering, I should go like that. Right. So we have 4 LMIs, 1 for each choice of delta. So in order to prove quadratic stability, we plug these this value of delta in. That gives us an LMI. Then we plug this value of delta in. We get another LMI, which we append to the original problem in YELMIP, add additional constraint. Then we add an additional LMI constraint, and then we add a 4th additional LMI constraint. Of course, if there are 3 parameters, we would have 8 of these. If there were 4 parameters, we would have 16. Right? So basically, you have to add an LMI at each possible extremal value of the uncertain parameters. And that can lead, if depending on how many uncertain parameters you have, to a relatively large number of LMIs, of course. Okay. But it's necessary and sufficient because it simply uses the theorem we had on the previous slide, which says that this is a convex hull, and therefore the LMI holds over every point in the hull if and only if it holds at the vertices. You notice that these results are only for the case where we have this linear or affine, depending if you think about it as that way or this way, this linear affine representation of the uncertainty. Right, so in terms of additive representation where the deltas don't multiply each other. If you have deltas multiply each other, that's a whole nother cup of tea, if you will. All right, so now that we're here, everything else really just falls into place relatively quickly. So for example, if you want the stabilization, right, an LMI for robust stabilization, here we're going to add some uncertainty to our B matrix, right? So again, B plus, let's say we have B equals B naught plus B1 delta 1 plus BK delta K. Right? Again, this is the polytopic case, right? The interval case, of course, is a straightforward extension of the polytopic case, right? So instead of enforcing the LMI condition at the vertices of the polytope, you enforce it at the vertices of the hypercube, right? So anyway, so we have an uncertain system. We have now uncertainty in our B matrix as well. However, nothing other than that really changes. So we've got this is our stabilization LMI. It has to hold at all of the vertices, right? So these BIs, right? And right, it's just the same except we have A plus delta or A plus AI and B plus BI, right? And likewise, if you can solve this LMI, if it's feasible, then you can get a controller in the same way we did for stabilization. K equals ZP inverse. And that controller will work for every value of the uncertain parameter, whatever it happens to be, even if that uncertain parameter is time varying. And that's important because this is a quadratic stability result. And so it allows the parameter to be time varying. I have a little caveat here, right, which says that note that because we this one controller and this one Lyapunov function are holding for every value of the uncertainty set, like all sort of quadratic stability results, it's a bit conservative, especially if the parameter is not time varying. So if you actually know what your value of the uncertain parameter is, it would be better to design a controller for it. But of course, the whole point of uncertainty is that you don't know what that uncertain parameter is, and even if you did, it would be hard to measure in real time, and so, even if you did and you designed a controller and the parameter was time varying, right? Then again, when we get back to this, we're getting back to robust stability. Robust stability doesn't work with time varying controllers. So anyway, basically, quadratic stability is the default tool we use in robust control. We relatively rarely go back to the concept of robust stability. Quadratic stability is by far the more common, and that's just because because the system is uncertain, right? Because we just don't know. We can extend these results in many directions, basically to almost all of the LMIs we've developed so far in the course. So, for example, here's one for destabilization. Right? Like the previous LMIs, these have to at every vertex of the polytope, we get another set of LMIs. So this is remember, this is the one for, I believe this was rise time, TR. This one was settling time, and this one was percent overshoot. Right. So really remember, these destabilization results constrain the eigenvalues of the closed loop system to lie in a specific region. So basically what we're saying is that if you solve this LMI and you reconstruct your controller using k equals zp inverse, then the pole locations of the closed loop system for any value of the uncertain parameter, assuming it's not time varying, satisfy the rise time, the settling time, and the percent overshoot constraints. Right. Now, so that's useful. Of course, this result also works if your uncertainty is time varying, as all quadratic destabilization results do. However, you can't really say anything about the eigenvalues of a system which is time varying, or at least you certainly can't relate them to any performance metrics, any system performance metrics such as rise time, settling time, and percent overshoot. So we can't really say anything. You can maybe wave your hands a lot and say, well, maybe it should probably, hopefully perform, and then you can test it, and so on and so forth. But I would be relatively cautious, because really what you're doing here is you're mixing a representation condition, right, for the eigenvalues of the representation with an LMI / quadratic stability condition, and you're trying to extend that to system performance. And that connection is very, very dubious, right? So we remember, quadratic stability tries to go directly to system performance without going through robust stability and representation eigenvalue stuff. So again, interpret this with caution, and probably don't use it. Next, we can get to optimal control. And optimal control in the H-infinity sense actually does still work, right? The transfer function for a time-varying system is meaningless, right? So time-varying systems don't have transfer functions. Don't have transfer functions. So why are we talking about H-infinity, right? If we don't have a transfer function to take the H-infinity norm of it. So perhaps, I should be saying more like L2 gain, right? The L2, the norm of the closed loop system in the linear operator sense from L2 to L2, right? I should really be saying that. But H-infinity is synonymous really with L2 gain, and hence we often just use the shorthand for H-infinity. But technically, this is saying this is H-infinity is wrong. Although it's true if the uncertainty is not time varying. So this is wrong if the delta is time varying. It's not. So the word what I emphasize, the word H-infinity there is wrong if the system is time varying. Right. So I think here, let me just skip forward to the notes here for a second. So So first of all, extending now our system with uncertainty to uncertainties now, not just in A, not just in B, which before was B2 actually. Well, that's what we had before, B and A. Well, now we're adding a different B, which represents the exogenous input. We have an output, which is actually probably Z, which is our regulated output. And for that Z, we have uncertainty in our C matrix. We have uncertainty in our D matrix, which measures exogenous input, and our uncertainty in our D12 matrix, which accounts for the effect of U. And of course, we typically do have that D12 there because we want to minimize the effect of minimize the size of the actuator signal. All of those uncertain parameters that we see in this representation have the same polytopic, or if you're doing interval uncertainty, polytopic/interval representation. So it's a combination of a bunch of vertices, right? So now, if these are interval, if this is interval uncertainty, right? Right, where we got AK delta K, right? We just need to like flip the switch on all of these A's to get all of the different LMI conditions. But hopefully you can do that yourself, right? So 2 to the K LMIs for interval uncertainty. So here we go. So we close the loop on the system, right? If we close the loop on the system, we got our normal closed loop system, right? This is the nominal, and we have the delta, right, which is the values of those so the value of the vertices of the polytope, right? So this is an infinite dimensional LMI, right, because it has to hold at every value in the polytope, but we represent the polytope using a finite number of vertices. Right? So basically it says that there exists a H infinity optimal, or L2 gain optimal, I should say, state feedback controller. If this, you can obtain the H infinity or L2 gain optimal state feedback controller by solving this LMI and then reconstructing your feedback gains using the same normal variable inverse substitution, F equals ZY inverse. Right. So basically this LMI has to hold at all of the vertices, right? So here we just added, it's the same LMI, but we've just added the each vertex to the appropriate term. Right. So again, if it's a polytope with k vertices, then this is a set of k LMI constraints. If it's an interval uncertainty case, right, then basically you have to do a plus and a minus for every I. So you have to construct all the vertices, right? So it would be, for example, with AI, right, it would be AI or A1 negative A1, right, if we had delta, and then A2 if that's the second delta, so if there's two deltas, delta 1, delta 2, so A1, negative 1, A2, A1, negative A2, negative A1, negative A2. Right. So for the interval case, so you would solve this LMI for every pair there. Right. Again, there's not that much to say here, right? It's a result. It's relatively easy to understand, relatively easy to enforce. Given the LMI we have for controller synthesis, the generalization to robust control is almost trivial. And this is true of many results in LMIs, and that's one of the reasons we use LMI, because the extension to robust control is so straightforward. Likewise, we can do H2 optimal state feedback, right? The same way. We take the LMIs we had for H2 optimal control, right, and we enforce them at the vertices, right? So these are our nominal LMIs for H2, and then we're adding on the uncertain equivalents, right? Just so these parts stay the same for every value of I, and of course these are the various vertices of the polytope, or the corners of the hypercube, if you prefer, depending on which one you're doing. I state these are all polytopic, right? But of course the extension to interval uncertainty is straightforward. Now, of course, again, right? If we're time varying. If we're not time varying, right, then for every given value of the uncertainty, your H2 norm will satisfy this inequality. Good. Now, if the delta is time varying, however, unlike the H infinity case, there's no real physical interpretation to the H2 norm. So you can't really say much if delta is time varying. I mean, you could like wave your hands, right? But again, there's no transfer functions for time varying systems. And so if we say this is H2 optimal, what do we mean? Which H2 norm is bounded by gamma, right? I mean, is there a transfer function whose H2 norm is? No, because there's no transfer function. Because the system is time varying, and time varying systems don't have transfer functions. So again, right, we can wave our hands. Possibly the LQR interpretation of H2 would still hold. So the special case of H2 optimal control where we're finding the LQR still works. But the noise interpretation does not. The impulse response interpretation, which we didn't go over, also does not hold. So time varying uncertainty in any case, we really shouldn't be talking about H2 norms too much, right? But we still do, because we have some intuition, hopefully at this point, as to what H2 norm means in terms of system performance, and we just hope that this extends in some way to time varying uncertainties. So this is controller synthesis. We can also do optimal estimator synthesis. If you go to the book, the LMI is given in Dwan and Lee. It's just, I don't know, it's so straightforwardly similar to the controller synthesis case that I just didn't bother writing it down on another slide. So, right, this is controller synthesis for H2 and H infinity, and right, I think you can figure out what the ones for estimator design are as well, if you'd like to. And then, of course, if you like, you can combine the robust controller with a robust estimator and get something which is maybe robust-ish, but again, no performance bounds. However, unlike the optimal control case, unlike the optimal control case for H infinity H2, where we were able to design an LMI for full state feedback control, the LMI in this case does not extend in a straightforward manner, I believe, to the full state dynamic output feedback case. That LMI does not extend in a straightforward manner to the polytopic uncertainty case, simply because there's too many variable substitutions that happen. Right, the parameters show up in weird ways, and so it's not as directly extendable. So dynamic output feedback, truly H infinity or H2 optimal dynamic output feedback, we don't have a result. All right, so that's again, right, in like, I don't know, how many slides? 5 slides. We were able to extend basically all the LMIs from lectures 8 through 11 to the robust case, just through that very simple way of enforcing LMIs at every point in a polytope, and by extension every point in a hypercube. Right. And just for completeness, this also works for discrete time, right? So if your discrete time system given here, right, here we don't have the output, but I'm sure if you wanted to do it, you could. Right, we have uncertainty in our update matrices. That uncertainty is polytopic, and we can enforce the equivalent of quadratic stability, which is that there's a single Lyapunov function, which proves sureness for every LMI. Although, again, our definition of quadratic stability needs to be redefined in this case. But I think you can figure what that is, right? There's a single Lyapunov function which works for every value of the uncertainty. But this is an LMI. It's if and only if, right? So no conservatism there. This is for stabilization in discrete time. Stabilization in discrete time. Right, discrete time stabilization. So if you can find a z and a p, or x in this case, such that this, here that should be x, so that this LMI is satisfied at every vertex of the polytope, then this feedback controller will stabilize the discrete time system, even if your uncertainty varies within the polytope with iteration with k. So this was this lecture covered the easiest part of robust control, right? And really, there were a lot of results, and there continue to be a lot of results in this area. I hate to say it, but possibly just because they're relatively easy to get. People are always trying to extend this in various directions, and with good reason, right? It's relatively easy to do, and it works fairly well. However, right, unfortunately, our uncertainties do not always have this form, right? They're not always additive. Sometimes the uncertainties multiply, and in that case, we can't. These results just don't work. There are SOS results, which are sort of extensions of this, but in general, the power and the necessary and sufficient conditions we went over in lecture 13 don't hold when you don't have this additive linear representation. In that case, we have to move on in our next lecture to the LFT framework, the more general framework, which has conservatism associated with it. It's not. The results are a lot harder to interpret, and it's not as necessary and sufficient as in this case. But it, of course, also covers a lot more cases and is much more general. So we'll come back to that in lecture 14. At this point, I'll close up the lecture and sign off, and I'll see you all next time.